Seismology really is the killer application when you get right down to it. It's the only methodology that we have to remotely study the deep interior of the Earth with any kind of resolution.
Today, Rick is blowing up a ton of high explosives to generate seismic waves.
Although it's on a small scale, it's exactly the type of thing that we would need to look through the interior of the entire planet.
Three seismographs have been set up. One just meters away from the explosives. Another at 1 kilometer distance. And the third 2 kilometers from the blast. They'll measure how the Earth moves in response to the detonation.
Typically with these shallow explosions, most of the energy actually goes into the air. What I'm interested in is how much goes into the Earth.
5, 4, 3, 2, 1.
Always impressive. There's no doubt that that sent a lot of energy into the ground. I think we'll see a very strong signal from this explosion.
This is what you see when you set off 1 ton of explosives. A supersonic shockwave. But, hidden from view, a second pressure wave is traveling through the Earth. A seismic wave. And it's what happens to this wave underground that Rick is interested in.
Very close to the explosion, we see a very simple signal. We see the seismic waves generated as a very sharp impulse traveling through the Earth, passing the seismograph, and it's all over in just a second or two. At 1 and 2 kilometers, we see the development of a very rich wave train of scattered energy, scattering off the topography of the landscape and scattering off the interior of the Earth, so that the signal is drawn out from this strong signal that was generated at the site.
The further seismic waves travel, the more revealing they can be. Because the speed at which they move through the ground changes depending on the constituency of the material they pass through.
The speed of the wave tells us basically how stiff the rocks are. And that can tell us a lot about what's going on within the Earth. If you're studying a volcano, for instance, the speed of seismic waves slows down tremendously when it goes through magma as opposed to rock.
But to create seismic waves, which are able to pass all the way through the center of the Earth and out the other side, you need seismic events bigger than this one. Earthquakes. The shockwaves of major earthquakes radiate through the globe. Scientists have gained a form of X-ray vision into the heart of the Earth by analysing the speed at which they travel. And it's revealed that we aren't simply living on one solid chunk of rock. The Earth is made up of different layers. First is the Earth's thin crust.
The Earth's crust is really, really thin. It's about 0.3% of the way to the center of the Earth.
Then there's the mantle, made of rocks turned malleable by the extreme heat and pressure.
The Earth's mantle is made of rocks that are in some ways similar to what we see at the crust, although their chemistry is a little different.
But then the waves hit something else, and, crucially, they slow down. To a seismologist, that could only mean one thing.
The fact that seismic waves travel down through the mantle in a certain manner and then they hit the outer core, which has a much slower seismic velocity, indicated the Earth had a core, and indeed it had an enormous core, and it's molten. It has a viscosity that's not much greater than water. So it's an enormous ocean of white-hot molten metal.
Seismology has managed to reveal the Earth's core. A huge sea inside our planet, the size of Mars.